So why would you use YUV? Well, okay, it's easier to cluster pixels, but you know what? That's not that important because I could just rotate those filter boxes. There's a much deeper reason, and that actually comes from the part that I showed you earlier. You remember that human vision is much more sensitive to changes in luminance than changes in color? What that means is that you could actually subsample the color, have fewer pixels, if you will, than luminance, and for the human system, it would be about the same amount of resolution. Okay? So in order to compress your imagery, in order to use fewer bits to describe something, one of the things you can do is you can use more bits for the Y channel than you do for the U channel and the V channel. There's an example, it's called YUV 422. I think the original 422 actually had to do with the amount of bandwidth of the luminance versus the two chroma channels. These days, when you think of 422, the idea is that if you were encoding 2 pixels, you would use 2 bytes of it, and assume that you were just doing pixels 0 to 255. You would use 2 pixels for the 2 bytes for the luminance, but 1 byte for U and 1 byte for V. So you had twice as many bytes dedicated to the luminance signal than you do the chroma signal. And it turns out that humans, it's pretty indistinguishable. Something else that you can do, there are other chroma spaces. Some of them come from video and television. There's one called YCBCR. Difference between luminance and blue, luminance and red. There's something called PB and PR. There are all these sort of different linear combinations. There's the LAB color space that was based upon the human measurements that we talked about before. There's something called LUV, which is just a little bit easier to compute than LAB. The bottom line is that all of these are different ways of representing colors. If I were to plot this now in, say, HSV space, right, and I just showed you H and S, right, hue and saturation, now it's pretty easy to find the red pixels, right? Here they are, there's some over here, some over there, all right? And the hue gives you the color spectrum. Why is this coming around back over here? It's because hue is actually going around in a circle and it crosses 0 there, so these two are actually very close together. One last thing, just if you ever want to play around, if you ever have a digital video camera, and you bring that video into your computer, and it's kind of like low light, you'll see it does a reasonable job. If you can pull out the R, G, and B signals and play them as a separate video, the R one will look okay, the green will look okay, the blue one will have all of this noise in it. You play it and it's awful. And that's because they dedicate hardly any bits at all to encoding the blue signal because it doesn't matter to you. All right? And again, this isn't physics, this is psychophysics, but it's how computer vision and computing of color relates to color.